Hello, everyone. I'm excited, as usual, to introduce our champ speaker this week. We have Takumi Murayama from Princeton, who will tell us about uniform bounds on symbolic powers in regular rings. Takumi.
Great. Well, thank you very much for having me here, and thank you for inviting me to speak in the seminar. Before I begin, I want to start with a land acknowledgement. So I recognize I live and work on the ancient homeland and traditional territory of the Lenape people, and pay respect to Lenape peoples past, present, and future, and their continuing presence in the homeland and throughout the Lenape diaspora. But with that, let me get to my talk. So today I'm going to talk about uniform bounds on symbolic powers in regular rings. In particular, I'm talking about my solution to an open question due to Hochster and Huneke about what the title says, and it's been open for 2 decades. Before I begin my talk, let me give you a brief outline about what the talk will be, at least the organization of the talk. First, I'll talk about symbolic powers and the containment problem. Then I want to give you kind of the idea of the type of proof we'll want to mimic by showing you the proof in equal characteristic 0. And then the last thing I'll do, I'll tell you some ideas from the proof of the main theorem. But of course, you could always read the paper if you want more details. But with that, let me get started. So let me start by talking about symbolic powers and the containment problem. Oh, and then the other thing I should mention is I do have the chat and participants window open. So if you want to ask me questions privately, you can do so through the chat. And of course, you can always unmute and ask me as well. Okay. And so what I want to do is I want to start with an example that kind of motivates where symbolic powers comes from. So let's consider the following ring. And please tell me if you can't see me right or if I'm writing too small. Where you take a polynomial ring in 3 variables over a field, and you take the quotient by x, y minus z squared. Okay. And so I guess I like to draw pictures. So this is what's called the coordinate ring of a quadric cone. And let's consider one of the rulings of the cone. So if you think about this geometrically, you can take a straight piece of metal or something and rotate it around the axis and you get this shape, right? So let's take P to be one of those lines that you can generate the whole cone by. Okay. Then I can highlight this in red here. So this corresponds to one of the lines on side of the cone. So this is a prime ideal. Okay. And so what happens if you square the prime? So if you take p squared, well, you can just compute what p squared is. It's y squared comma yz comma z squared. But we know that xy equals z squared in this ring. So this is y squared comma yz comma x squared, or xy, sorry. And one thing you'll notice is that this ideal is no longer primary. So I wrote p primary first, but it's not p primary. And you can write down the primary decomposition. It ends up being y intersect with x comma yz comma y squared. Okay. And so maybe I'll draw the picture for what I have in mind when I draw this picture. If you look at the vanishing locus of y and z in this picture, you get this ruling. And if you take p squared, you get this sort of, squiggly line union with an embedded component at the origin. And so what's going on is that when you take the square of the ideal, you're getting a bit more geometric information that you might have expected just by judging by the picture. And so this leads to the idea behind symbolic powers, which is due to Krull in 1928 when he was trying to prove the height theorem, which is that you can enlarge p squared so it is p primary. Okay. And the way you do that is you introduce this notion called symbolic powers. So let me define it for you. And I'm going to give one definition, and I'll tell you a bit afterward that there are some variants. So let's let R be a Noetherian ring, and let's consider an ideal I inside of it. Then the nth symbolic power of I is the following ideal. We denote it by I parenthesis n. And what you do is you expand and contract when you localize at each prime ideal. So I'll say that out loud, but really what I mean is you do this. Right? So you localize at each prime associated prime of R mod I, you extend I to the n to that ring, and then you contract it back to R. At the very end, you contract all of them together. And maybe I'll point out that there are other possible definitions. So for the experts, you could take minimal primes instead of associated primes. There are certain situations where you want one over the other, but at least for the kind of questions I'll talk about today, this is the more convenient definition. All right, are there any questions about the definition of symbolic powers? Okay, and so let me tell you a few things about the definition. First of all, I said that Krull invented them to try to fix this p primary issue. And that's in fact true. If p is prime, then the nth symbolic power of p is p primary. Right? One way to see this is that in the localization, now you're just taking powers of the maximal ideal, in which case the symbolic powers are the same as the ordinary powers. And then if you contract a primary p primary ideal, you get a p primary ideal. Okay. The next one is that one reason why we want the associated primes definition is that the first symbolic power is the original ideal. The third thing I'll say is that since I to the n is contained on everything on the right hand, or I guess right, by definition, you have this inclusion that ordinary powers are always contained in symbolic powers. And the last one is that if you increase the power on I to the n, then we get smaller and smaller ideals. And so I guess these are the four properties I want to point out about them for now. But now I can state the containment problem. So one of the key things I showed you here is that there's a nice relationship between ordinary and symbolic powers. Symbolic powers are always larger. And so a natural question to ask is, when do you have an inclusion in the opposite direction? And so I think this is the first time I did this, but I'm going to scroll on alternate sides, left and right, so that you can see the previous slide, so to speak. So hopefully this gives you at least a way to keep track of what's going on. Okay. So what is the containment problem? Basically, it asks, when do we have the opposite inclusion? When do we have the symbolic power contained in the ordinary power? And I guess I'll point out that, the numbers here can differ. Like you can have a much larger number m that works instead of n. And this problem has quite a lot of history. I'll only say some of it though. One of the earliest places where this was considered was by Zariski in 1951. And let me just state this theorem for you because it gives you some idea of what kinds of things influence whether this sort of containment problem holds. So let's let R be a Noetherian domain. And let's assume that all its local rings are analytically irreducible, which means that if you localize and complete at each prime, you get a domain. Okay. And what did Zariski prove? He proved that for all p and for all n, there exists some m such that p to the m is contained in p to the n. Right? So he was able to show that these two systems of ideals that get smaller and smaller are cofinal. And the concise way that you can say this is that the topologies defined by these two systems of ideals, p to the n and p symbolic n, are equivalent. And so you could, then you'll wonder, we know this is true for these primes inside of rings that are domains, such that all the localizations give you domains as well after completion. And Hartshorne asked, can you characterize all possible rings that look like this and have this topologies being equivalent kind of property? And this is true, and this was proven by Schenzel in 85 and 86. So Schenzel characterized when exactly these two systems of ideals are equivalent for arbitrary ideals I. And so for the experts, if you look at the paper, he doesn't quite state it this way and doesn't have this definition of symbolic powers, but after some work, you can deduce it from his result. Okay, are there any questions about Zariski and Schenzel's results? Okay, so in particular, Schenzel's result does recover Zariski's. Okay, so now we kind of have an idea for when they're equivalent. And then you can ask, okay, how does this equivalence actually come about? Is there a nice way we can relate the two topologies? And this is true. And this is due to Swanson in 2000. So let me state her theorem. Let's let R be a Noetherian ring. Swanson's theorem says that if the system of ordinary powers and symbolic powers are equivalent, this holds if and only if there exists an integer k such that the knth power of I, symbolic, is contained in I to the n. Okay. And so not only do we have an equivalence of topologies, but it's related in a nice linear fashion by basically a slope on the n. However, you could ask, what is K? So if you have a ring and you have an ideal for which we know these are equivalent, can we actually tell you what K is? And the other thing is, does this actually depend on the ideal I, right? So if you look at Swanson's proof, there's not an explicit description of K, and there's also not an explicit way to understand whether this K might change as the ideal changes. And the main topic for today is that there are good answers for regular rings. Starting with the following theorem. So this theorem is due to Ein, Lazarsfeld, and Smith. For smooth complex varieties, and Hochster Huneke for all equal characteristic regular rings. So if R is regular and of equal characteristic, and I is an ideal inside of it, then we have that the dnth symbolic power is always contained in I to the n for all n. Where here, d is the dimension of R. Okay. Are there any questions about their theorem? So maybe I'll say why it answers this question I wrote above, is that if as long as R is a regular ring and it contains a field, that's what equal characteristic means. It says that you can just choose K to be this uniform number D, the dimension of the regular ring, as long as it's finite dimension. And this is really an interesting theorem because the proofs use different techniques. So the Ein, Lazarsfeld, Smith proof uses multiplier ideals and ideas from complex analysis, whereas Hochster Huneke used tight closure. So I'll talk more about the proof techniques later, but for now, I just wanted to point out that the way that you prove these are quite different. Okay. And before I state my main theorem, let me tell you a few things about this number D. You can ask, can you choose D to be smaller? And you can. So you can replace D with what's called the big height of I. So this is the maximum height of an associated prime of I. Or you can even choose it to be what I'll call H in the rest of the talk, which is the largest analytic spread of the localizations of I at the associated primes of I. But if you don't know what these are, it's okay, because you can always just take the dimension. Okay. And so what is the question I wanted to answer? So in their 2002 paper, Hochster and Huneke asked, does this theorem hold in mixed characteristic. In other words, does it hold if you don't assume that your ring contains a field? And as a result of recent developments in, perfectoid geometry, Schwede proved that yes, this is true. Under some assumptions. So they can prove this is true for radical ideals in excellent regular rings. Okay. And for the experts, you don't really need the full strength of excellence. You just need that it has geometrically reduced formal fibers. But in any case, there are extra assumptions on the ring. And what I proved, and I'll state my main theorem in a second, is yes. The answer is yes, in general. Okay. So now let me state my main theorem. Okay. And so I guess I'll put my initial here, but this is special cases are due to Ian Lazarsfeld Smith and Hochster, Huneke, and Schwede. So please keep that in mind. I'll tell you what exactly is new in my theorem in a second. So if R is a regular ring and I is an ideal inside of it, then we always have that the h-nth symbolic power of I is contained in I to the n, where h is, the dimension of the ring, or one of these two other types of h's that you could take, the big height or the analytic spread. Okay, and let me tell you what exactly is new. So it's new when R here is not necessarily excellent, and when I is not necessarily radical. So I'll tell you why these assumptions exist in Schwede later, but for now, that's what I'll say. Okay. Are there any questions about my main theorem? Okay, so I'm probably going to need to have the statement later. So let me copy it into my clipboard. And so this gives a complete answer to this question of Hochster-Huneke. And also, let me point out one corollary that I think is kind of interesting, which is that if R is a regular ring of finite Krull dimension, then R satisfies what's called the uniform symbolic topologies property. So basically, this is just saying that the K that shows up in Swanson's theorem can be chosen uniformly for all ideals inside of your ring. I forgot the word symbolic. It's USTP. So this was defined by Huneke, Katz, and Valadash. Okay. I do want to say, though, that I don't only prove this main theorem in my paper, so let me give you two stronger results that I also prove. And these are completely new in mixed characteristic. Okay. So again, this is true already in equal characteristic. What's new in my paper is a mixed characteristic case, so I'll tell you where those come from in a second. But if you have a regular ring and I is an ideal inside of it, and we choose a bunch of integers S1 to Sn, and let S be the sum of those, there's two more things we can say, which is basically saying if you change you can, I guess, right, it involves products of different symbolic powers of I. So first of all, I symbolic S plus NH is contained in this product of a bunch of other symbolic powers. And the other thing is that if R is local, then I to the S plus NH plus 1 is contained in the maximal ideal times the same product of symbolic powers. These two results are in equal characteristic are due to the following people. Some special cases are due to Hochster Huneke, but the full statement is due to Johnson. And B, this is due to Hochster Huneke in 2007, Takagi Yoshida in 2008. And again, the full statement is due to Johnson in 2014. Okay. Great. Are there any questions about these stronger versions? Yes, Carrie.
Just really, is the Johnson, is that Mark Johnson or?
Yeah, that's right. It's Mark Johnson.
Okay, thank you. And in item B, what is the symbol in front of the product? I'm sure you said it, but
oh, it's the maximal ideal.
Thank you.
Yeah.
Thank you.
It's always hard to write fractor on a chalkboard or iPad.
Thank you.
Yeah, thank you. Okay. And I'm not going to talk much about these two stronger versions. I will say, though, that they do have applications. For example, A has applications to Louisa's version of the Harborne conjecture, so the asymptotic version of the Harborne conjecture. And B is related to a conjecture of Eisenbud and Mazur. But if you have more questions about these applications, you can always ask me after the talk. Okay. And so before I talk more about the proofs and what we want to do, let me say kind of the point of the rest of the talk. So how was I able to resolve the Hochster-Huneke question? And also how was I able to obtain these stronger results than what Ma and Schwede could do? So there are two things. First of all, I defined a new version of perfectoid / big Cohen-Macaulay test ideals. And if you don't know what those are, I'll talk about them later. And second, the way that I prove properties of these test ideals really use recent developments in mixed characteristic, commutative algebra, and algebraic geometry. But with that, what I want to do next is kind of tell you how you would prove my main theorem equal characteristic 0 and the type of proof strategy we'll want to use. Okay, are there any questions before I move on? Okay. So how does the proof go in equal characteristic 0? So let me paste here my main theorem again. So if R is regular and it contains an ideal, we can always include the hn symbolic power instead of I to the n. Let me show you a proof when R contains the rational numbers. So when it's of equal characteristic 0. So this mimics the Lazarsfeld-Smith proof. I'll point out, though, that at least the way I'm writing it down, you do need some of my work. Okay. So to prove this in equal characteristic 0, what can we do? So first of all, you can reduce the complete local case. And second of all, well, I guess I should say that you can reduce the complete local case basically because, symbolic powers, also associated primes, all behave well under faithfully flat maps. You have to worry a bit about some things, but in any case, this is true. And the insight of Lazarsfeld and Smith is to use these objects called multiplier ideals. So I won't define them for you, but I do want to give you an idea for how they're used. And I'll show you how they are used, I guess. Which is that what you do is you plug in an ideal and some sort of rational number t. And the way that I like to think of this is that it allows you to take nth roots of ideals. Okay. And so how does this proof work? So this outline will show up later again. when I do it for test ideals, but let's try to see what happens. So we have the hn symbolic power of I. The first property we need about multiplier ideals is that if you plug in an ideal, it gets larger when you plug it into a multiplier ideal. And Schwede called this property not too small. Okay. The next property you need is that you can replace this 1 here with n over n, and it's not going to change anything. So Schwede called this property unambiguity of exponents. So it doesn't matter how you write down the rational number. The third thing you need is that you can pull out the n on the numerator. Oh, I forgot the 1 over n there. So let me put that back in. 1 over n, and then match the parentheses correctly. This is called subadditivity. And the last thing you need is you need to include the thing inside the parenthesis instead of I. And Schwede called this not too large. Okay, and so let me draw a black box here, because this is how the proof goes, at least in outline form. You use these formal properties of multiplier ideals, and in each step, there's a lot of things you have to prove. But if you want to do something similar in positive characteristic or mixed characteristic, you might wonder, is there some way you can attach an ideal to an ideal in a rational number that has formal properties that are similar to multiplier ideals? Okay. Are there any questions about this proof outline? Okay. So let me give you a couple remarks. So here I said that this works if you work for any regular ring containing the rational numbers. As I said before, the Lazarsfeld proof works for complex varieties. So you need my vanishing theorems to do part 4 in this proof. At least in the generality I stated. Okay. The other thing, I guess this is more a comment for experts, but the other way they can prove this statement in equal characteristic 0 is to do what Hochster and Huneke did, which is to use type closure and Artin approximation type arguments to reduce modulo P. The way that you do that, though, uses Artin approximations type arguments. And so at least this argument does not use Artin approximation. So this was something that Schoutens asked in 2003. Okay. All right, great. So now I can tell you a bit about why we can't do the same proof in positive or mixed characteristic. So if we want to define or use multiplier ideals, we need 2 tools from characteristic 0 algebraic geometry. The first one is resolutions of singularities. And the second one is vanishing theorems. And I won't talk about the history too much, but in any case, in positive characteristic and mixed characteristic, they're either unknown or false. And so the approaches we have now are to replace multiplier ideals with something that is more closely mimics ideas from positive characteristics, such as type closure. So Hara in 2005 and Schwede in 2018, and then I guess myself, because I made this strategy work. The idea behind our proofs is to define a variant of multiplier ideals called test ideals, and they're usually denoted by tau r, to replace multiplier ideals in order to prove this theorem of Lazarsfeld-Smith, Hochster-Huneke in mixed characteristic, or even positive characteristic. How do you define these things? So in positive characteristic, test ideals are defined using the Frobenius map. And in mixed characteristic, defining them requires perfectoid techniques. Okay. And so if Schwede were, since the Schwede theorem does have an assumption on it, you might wonder where in this strategy does their version of test ideals not work? And that happens in step 4. Because they need to compute this test ideal, tau r of I to the hn symbolic power nth root. The way they do this is to compare it with the multiplier ideal, and then they do some discrepancy calculations after taking a normalized blowup. So that description, I guess, is a bit complicated, but I thought I should tell you that it is something that they really need to use. And the other thing I want to mention is that the radical assumption really is intertwined with this condition on the excellence of the ring. So assumption on excellence is needed to make sure that I stays radical. Okay. And so to prove the full theorem, to prove my main theorem, we do need something new. Okay. And to tell you what we need to do, let me tell you 2 more things that you actually need about multiplier ideals in characteristic 0 that enable you to prove part 4. Okay, so I'm going to call these 4a and 4b. 4a is that multiplier ideals are known to localize well. So if you take j of r comma I to the t and you localize it rp, this is equal to j of rp I rp to the t. So again, I guess this is an equal characteristic 0. I should make that clear. And the second thing that you need is what's called Škoda's theorem. So if Škoda's, for us, I guess, is famous for the Brillouin-Škoda theorem, and this is related to those types of results. Škoda's theorem says, if you have an ideal j instead of I, and it's generated by h elements, such that their integral closures are the same, then you can pull out a copy of j from the multiplier ideal. And so these were 2 missing things that we didn't know about test ideals and mixed characteristic. What I want to do next is to show you what we have available in mixed characteristic so far. Okay. So for what I say now, Rm is going to be a regular complete local ring. And we're going to consider an ideal generated by F1 through Fn. And I would draw this whole table for you, but it's faster for me to just paste it from what I wrote earlier. So let me just do that. Okay, so that was quick. Let me kind of tell you what's going on this table though. So as I told you before, in the Schwede proof in 2018, they invented these things called perfectoid test ideals. And the notation is written down this way because it really depends on the set of generators F1 through Fn. Okay. For their theorem, they were able to prove that it's not too small, that it satisfies this unambiguity statement, and it satisfies subadditivity. So 3/4 of that proof are all, they work perfectly fine. As I said before, though, at the last step, they use radicality. And what we don't know about it is that there's no localization type statement or Schwede type statement, at least that I know of, for these types of test ideals. So this means that the way that I would want to prove the number 4 using techniques from, the ideas from multiplier ideals, they don't quite work. Since then, there have been other developments in mixed characteristic commutative algebra, and this has involved different new versions of test ideals. So the one here is also due to Schwede in 2021. It's also related to a definition of Perez and RG in 21, and also extended by Sato Takagi later. But in any case, you can fix what's called a big Cohen-Macaulay algebra for R. I'll define this later, but we'll see it in section 3. And attached to that choice and the ideal I and the rational number T, this sort of big Cohen-Macaulay test ideal. This one has some nice properties. It's not too small and it's not unambiguous, but these 3 properties were still open for that one. Of course, there are other reasons you might want these, which I'm not mentioning here. But in any case, what I want to point out, though, is that last year there is a new version of test ideals to the Haken, Lamarche, and Schwede. And these are nice because they're not too small and they're unambiguous. We don't know they have subadditivity, but they do satisfy a localization type property for principal localizations, as long as you replace the ideal with a divisor. So, this will come up later in the talk, but I'll kind of just at least show you how that happens. And it does satisfy a Schwede type theorem. Okay, so now that you kind of see the landscape of test ideals, what you might notice is that there's no single column that has all check marks. So this kind of tells you that none of these are sufficient, at least to prove the main theorem alone. And so what was my idea? My idea was that I wanted to find a new version of test ideals that combines the advantages of all of these. Okay. So what I came up with is a definition I'll make later, but tau sub b of r comma f to the t. And it satisfies 1 through 4. Okay. Of course, though, I should point out that to prove that these properties hold from a test ideal, I will need to use properties of these other test ideals. So in particular, the Haken-Lamarche-Schwede version does come up in my proofs. But with that, what I want to do for the rest of the talk is talk about some ideas in the proof of my main theorem. So before I get into more technical details, are there any questions? Okay. So let's talk about some ideas in the proof of my main theorem. And so maybe before I get into the details, I will mention that I'll end up outlining proofs of all cases of the main theorem. So an equal characteristic as well. Although I will point out that the proof of 4 does, it does split off at that place. And so what's the key point driving the proof? So the key point driving the proof is that for multiplier ideals, I said that you need resolutions and vanishing theorems. They're either false or unknown in positive or mixed characteristic. But we do know that what are called big Cohen-Macaulay algebras always exist. And these serve as a replacement for them. So this is not my original idea. It goes back to the work of Hochster and Huneke, etc. But really, this is what's driving the proof. And if you don't know what big Cohen-Macaulay algebras are, let me just mention that they came up in Hochster's homological conjectures, including the direct sum and conjecture. So if you're wondering where the connection with these recent developments in perfectoid geometry come from in my talk, really it's because, we were able to resolve, the Andre resolved the direct sum and conjecture, and the perfectoid techniques used there also proved the existence of big Cohen-Macaulay algebras. And we are seeing further applications of these sorts of techniques as time goes on. So let me define big Cohen-Macaulay algebras because they are very important. So they originated in this paper of Hochster, I think in 1975. Although I'll give a variant of the definition due to Sharp. So let's let Rm be a Noetherian local ring. And let's suppose it's of dimension D. I guess I'm not using the dimension definition, but that's okay. Now let's let B be an R algebra. So we say that B is parenthesis balanced, big Cohen-Macaulay. So we'll abbreviate it BCM. If every system of parameters x1 through xd on R becomes a regular sequence on B. Okay. And so there are some variants of this definition. When I say a big Cohen-Macaulay for the rest of the talk, I will mean balanced if you worry about this type of thing. And let me tell you the key theorem here, which is that these always exist. And not only do they exist, but you can assume that they are in fact R plus algebras as long as you're a domain. So that's the version of the theorem I'll state. So this is due to, okay, maybe I'll just write down the theorem first. Every Noetherian local domain Rm has a BCM R plus algebra. So R plus here is the integral closure of R in an algebraic closure of its fraction field. And so if you don't want to necessarily have R plus be inside of there, you can just have, every Noetherian local domain still has a BCM algebra, but in any case. So this is due to Hochster and Huneke in 92, Dietz and RG in 2019, Andre in 18 and 20, and Shimamoto in 18. All right, so Hochster and Huneke proved the equal characteristic case, an equal characteristic P. At least explicitly, if you want this R plus statement equal characteristic 0, you should look at this paper of Dietz and RG. But then Andre and Shimamoto did the mixed characteristic case. All right, and these are kind of hard to get a handle on, but in specific cases, we know exactly what they can look like, or there are examples, you know what they are. So this is due to Hochster and Huneke and Bargov, which says that if you take the p-adic completion of R plus, this is a big Cohen-Macaulay algebra. For Noetherian local domains. I think actually I need complete local domains of residue characteristic P. All right, great. Are there any questions about big Cohen-Macaulay algebras? All right. So let me tell you my definition of a test ideal. So this mixes elements from Schwede 18 and 21. So if you have a regular complete local ring, And B is a BCM R plus algebra. And you have a bunch of elements F1 through Fn inside of here, and a rational number T. The version of test ideals I define looks like the following. You take the annihilator of a certain submodule of the local cohomology module with respect to R. Okay, so D here's the dimension. Okay, and maybe it's not too important what exactly this is. I'm just writing it down so I can point out some differences with the Schwede definition. So basically, we're trying to annihilate a bunch of elements using powers of these generators F. All right. And so for the experts, I guess I'll say that you don't need regular here. So you could weaken this to normal, and then as long as you put in some divisor delta, you can make sure that KR plus delta is Q Cartier. But in any case, this is what it is for regular ring. Compared to the Schwede definition, there are some differences, however. First of all, there's no almost mathematics involved. Second, I'm ranging over all integers M instead of just P powers. And third, I don't perturb these. So, these comments are really for those of you that perturbations are familiar with the Schwede paper. And the last thing I'll say is that it works in all characteristics. Yes, is there a question?
Yes. So we say you're dealing with your definition of regular ring, but you put the annihilator of mega R. Wait a second. I'm very confused.
Yeah, so it should just be R if the regular ring. Yeah. I just wanted to write down the definition. Yeah, because if I told you that it could work for a normal quasi-Gorenstein ring, for example, and if you read the definition, you get the wrong thing.
You're just using the notation.
Yeah. Yep.
Make sure nothing's misspoken.
Okay. Are there any other questions?
Wait. So even when you were indicating about this, your test ideals, so you just wrote, instead of writing down the ideal, you just wrote down the system F. So if I vary the system F, but it still generates the same ideal, and does the test ideal changes?
I guess I'll say that I'm pretty sure it could change, although I don't have an explicit example in mind.
Yeah. Thank you.
Yeah, and it's actually useful to fix a set of generators.
And I apologize. Actually, I didn't quite understand the definition of the test idea, like the one you gave. Could you please unpackage it a little bit?
Yes. So it's a bit complicated, but basically, if you thought about the definition of the test ideal in characteristic P, and there's one way to define it using traces of P inverse linear maps, right? Have you seen that definition? And if you take the matless dual of that, you end up getting things that look like certain annihilators inside of submodules of local cohomology. And so that's what this definition is trying to mimic, the definition where you take the annihilator of the tight closure of 0 inside of an injective hull or something like that. Although here we're using like the parameter version, so you get local cohomology instead. I don't know if that helps very much, but that's where the idea comes from.
Thank you.
Okay. All right, okay. And there's one thing I wanted to mention is that there's a key comparison between my definition and the other ones. So if you set B to be R hat plus in a residue characteristic P, then my test ideal is contained inside of a variant of the Haken-Lamarche-Schwede definition where you take divisors as your arguments instead of an ideal. So these two are different versions of the test ideal that appear in Haken, Lamarche, and Schwede. All right, and the reason why I want to state this is that now we can try to mimic the characteristic zero strategy by switching to this other ideal at the correct place. Okay. And now I have 2 more slides, but I guess it's almost my time is up. Is it okay if I go over a few minutes? All right. And so maybe I'll just say that the same strategy as before works with the multiply ideals, except for step 4. So I'm going to focus on step 4 for the rest of the talk. And so what did I prove? I proved that in the setting of the theorem, there exists some big Cohen-Macaulay R plus algebra B, such that R comma F to the 1 over n is contained in I. Okay, so proof. If R is of equal characteristic 0, we know that for any test, any B, we have this inclusion. And I guess here, F is the generating set for I to the Hn. Sorry, I did not make that clear. So the proof in equal characteristic 0 works. Okay, so what's remaining is the residue characteristic P case. And so what we want to do is we want to prove that this test ideal is contained in I. And to check that, all you need to check is that this inclusion holds at the associative primes of I, because otherwise, there isn't much to show. But the localization property we have is not for prime ideals, it's for elements. So instead we localize at X, that's not in P, such that the following 2 properties hold. First of all, there exists a reduction of I. And to do this, there is one reduction I didn't mention, which is that you need to reduce the case when you have an infinite residue field, but you can always do that. And you also need that the symbolic powers and ordinary powers of I are the same. Okay, so now I can finish the proof in a minute. Right, so as I said before, we're going to want to use R hat plus inside this definition to make it talk to the Haken-Lamarche definition. My key comparison theorem tells you that this is contained in the following large sum of a bunch of Haken-Lamarche test ideals. And it's a bit of a it's a bit difficult to see how this is all going to come together. But by just kind of thinking about what integers you're summing over and what elements you're summing over, you can replace, first of all, the symbolic power here with an ordinary power. And you can even remove this Hn by putting it inside the sum, because you're summing over more things now. Finally, since J and I are basically the same here, up to integral closure, there's a way you can make these look like this. You can replace I with J. By the Haken-Lamarche paper, or maybe I'll put J hat here, or J bar here. You can relate it to the ideal theoretic version, which satisfies the requisite Schwede theorem that we need. Okay. So sorry that was a bit rushed at the end, but I wanted to give you an idea for how this proof comes together. What I need to do is first of all have this new definition of test ideals and have it talk to enough of the older ones so that I can use the nice properties that those satisfy. With that, thank you very much for listening, and you can ask me any questions you have.
Let's thank Takumi for the nice talk. Questions?
Not really a question, but can you scroll back up to your definition, please?
The definition, okay, I'll go on the left then.
Of your test ideas.
Here you go.
I kept getting really confused. So the F sub J K. I see what you're doing.
Yeah, it's kind of hard to describe.
One to A, and A is bringing an M2. Okay. All right. So I kind of digest that slowly.
Yeah.
Okay.
Right. You basically take monomials in the Fs and take roots of each of the factors.
Okay. So I don't mess up explaining what you do to other people. Can I try to repeat information back that you just told me? Like if I was to try to share this paper with other people, can I try to summarize something?
Yeah, sure.
I want to make sure I don't get something wrong.
Okay.
Right. I just want to, right, so in terms of key ingredients, right, you come up with this definition, and then critical parts in your proof, right, it looks like you're saying like that first inclusion on that right page, the key part where you put some hard work into, but then also you need this HLS paper that gives these test ideals that actually start localizing to some extent and make characteristics. Those are like, I feel like two of the big ingredients going on here.
Yeah, so I think those are two big ingredients. So maybe one way that I think of it is that it would have been nice to be able to do this directly with the Mosh-Reed definition.
Of course. Yeah, I'm sure they wanted to as well. Actually,
yeah.
I know they wanted to.
Yeah. But there are these things that they said they have that made it hard to prove things about them. And so these first three things I mentioned because it allows me to prove these stronger versions of subadditivity and unambiguity that are really necessary to prove like the Johnson version of the symbolic powers result.
Sure.
Okay, so that's one big part. The second part is that I don't know whether the Mosh-Reed test ideals compare well with the other ones because of really this perturbation right here. Okay, so that's why I needed this new definition so it doesn't have to be perturbed. And then so I can prove this comparison lemma that I wrote down a few slides back from the end.
Right.
And lastly, that allows me to use the Haken-Lamarche results.
Okay.
I guess another nice thing I think is that
algebra as well, of course, and then of course the mixed characteristics.
Yeah, and of course, I also like that my definition works in arbitrary characteristic. So if you wanted to know why the Lazarsfeld, Smith, Hochster, Huneke, Mosh-Reed, I guess my name, theorem holds, my paper does contain proofs of all of them.
Oh, cool. That's nice.
Yeah.
That's nice. You just do it all at once. That's good.
Yeah.
I guess the HLS papers, and then I was thinking Takagi's paper showing that there was hope of going further, right? Because there was a unifying. Okay, so Takagi put 2 out of 3 together. You put all 3 together. Very nice. That's good. Thank you. I appreciate it.
Yeah, sure.
I have a
question
too, if there's time.
Go ahead.
Cool. So in your proof, do you construct the particular big Cohen-Macaulay algebra, or is it just like, well, we know there one exists?
So let's see. Okay, so for steps 1 through 3, it works for any big Cohen-Macaulay algebra, so it doesn't really matter which one it is, but you're right, I don't construct one, I just black box the fact that they exist. In this part 4 of the proof, in characteristic 0, any B works, but in residue characteristic P, I really need to use R hat plus.
Okay, cool. I was wondering if that was part of why it was sort of like characteristic specific, so thank you.
Yeah, right. So that's where the proof does diverge a little bit between the two cases, which is that, in characteristic 0, you eventually use multiplier ideals. In residue characteristic P, you use R hat plus.
Cool, thanks. And also, awesome job on making this topic, which gets so technical, something where people could understand the outline of your proof. Awesome.
Yeah, thank you.
All right, in the interest of time, let's thank Takumi again.
Thank you.